The paper titled Post-Quantum Asynchronous Remote Key Generation for FIDO2 by Jacqueline Brendel, Sebastian Clermont, and Mark Fischlin. And Sebastian will give the talk.
Mm-hmm. Is it on? Yeah. Okay, perfect.
Yep. Thank you, Sebastian.
Yeah, thank you very much for the kind introduction. My name is Sebastian Clermont, and this is joint work with Jacqueline Brendel and Mark Fischlin. Do I get a presenter or something? Perfect. Thank you. Okay, before diving into asynchronous remote key generation, I will start with some basics on FIDO2. So the FIDO Alliance is an industry alliance which was formed in 2012 with the goal of eventually finding a replacement for passwords, which allows for more secure and easier online login authentication. They have published a number of standards, with their most recent standard being FIDO2. In the FIDO2 standard, there are three actors. There is a security key, which is in the possession of a user trying to authenticate itself. There is a client or platform, which is the computer, for example, which the user is using to access some service. And then there is the relying party, which is the service where the user is authenticating. There are two protocols involved. There's the client to authenticator protocol, which handles the communication between the security key and the client. And there's the web authn protocol, which handles the communication between the client and the relying party. Both protocols together are standardized under the FIDO2 standard. I will now briefly explain how FIDO2, we're going to gray out the client platform layer and just look at from a logical level at the communication between the security key and the relying party. There is two different kinds of authenticators. There is the security key, which is a hardware device with cryptographic capabilities, which can generate secrets on the device and store them there. This is the more secure variant because cryptographic secrets never leave the authenticator, but are always stored securely there, and all cryptographic computations happen on the device. On the other hand, there are passkeys, which are not stored on a single device, but are linked to an account at, for example, Apple or Google, and are synchronized with all devices. This is a lot more convenient because you cannot lose the authenticator. On the other hand, you do not have ownership of your secret key and are never sure who actually ends up with this. So since we want to talk about recovery, we focus on the setting where there's a security key, where the secret keys cannot be exported. I will now briefly explain how FIDO2 works. So there is the authenticator and there is the relying party. And now the authenticator wants to register with the relying party. So it first generates a new and independent secret, sends the corresponding public key to the relying party. The relying party stores the public key and associates it with the user account and confirms the registration. During authentication, when the user now wants to log in using web authn, the security key has multiple secrets generated for different services. Here we're logging in to the green service. So the authenticator receives some cryptographic challenge by the relying party, chooses the corresponding secret key, and then a user verification process unlocks the secret key material. This is realized using some kind of personal identification number or biometrics. Once the secret is unlocked, a response is calculated, which is just a signature on the challenge value with some additional data, and is sent back to the relying party. If the signature is valid, the authentication is successful. Now, this works very well, but the problem is that all the cryptographic secrets are stored locally on the authenticator. So in case the authenticator breaks, all the secrets are lost, and an authentication is no longer possible as the secret key material is no longer available to the user. To tackle this, the primitive of asynchronous remote key generation was introduced in 2020 by Freeman et al. At CCS. I will now introduce this primitive. In asynchronous remote key generation, you have two authenticators, which are coined the primary and the backup authenticator. There is an initial pairing between the primary and the backup authenticator, which happens exactly once in the very beginning, where the backup authenticator generates some public key and transfers this to the primary authenticator. Then the backup authenticator can be stored in a safe place for safekeeping, while the primary authenticator can be used for registering and authenticating with services. So from the primitive level, there is an algorithm for key generation, which takes no inputs and outputs an initial public key and an initial secret key. Now with the backup authenticator stored safely somewhere else, the user can go ahead and use the primary authenticator to register at as many services as he likes. The FIDO2 registration works as normal, but there is one additional message from the primary authenticator to the relying party, which includes a derived public key as well as recovery information, which will later be used for the recovery. The relying party has to store this information and associate it with the user. This can happen multiple times, depending on the number of relying parties the user registers with. Note that all the public keys are independent of each other, and there's a new derivation happening each time. So it's a the PK1 derived up to PKN derived. And from a primitive level, there's an algorithm for deriving public keys, which takes some initial public key and outputs a derived public key with associated recovery information. Now, when the primary authenticator breaks and the user has to perform recovery, he now uses his backup authenticator. This is an illustrative example how this would work for one relying party. The user initiates the recovery by naming some identifying information like his username or his email. This allows the relying party to look up the derived public key and the recovery information that was stored during the recovery. And the relying party sends the recovery information and some challenge under the derived public key to the backup authenticator. Now, the backup authenticator can independently derive the secret key that is associated with this derived public key to assign the challenge and answer with a valid response. And the recovery is successful if a valid signature under the derived public key is returned. From a primitive level, there's an algorithm for deriving secret key, which takes as input an initial secret key, as well as recovery information, and returns the derived secret key that is used for calculating the response. So to summarize, there are three interactions. There is the pairing, which happens between a primary and a backup authenticator. There is a registration step, which happens between n relying parties and the primary authenticator. And in case the primary authenticator gets lost, there is the recovery step, which takes place between the relying parties and the backup authenticator. In our paper, we provide three key contributions. First, we update the security notions that were initially brought forward at CCS to more closely match the FIDO2 setting. We then provide a generic construction from standardized primitive, achieving the security notions, and then show the security of a generic instantiation in the post-quantum setting. So let me now introduce the security notions that we have introduced for the ARKG schemes. The first property is the authentication security. Authentication security's purpose is to ensure that no malicious actor can perform the recovery without being authorized, meaning only the backup authenticator should be allowed to perform the recovery. The adversary has access to several oracles. First, he can observe the initial pairing between the backup and primary authenticator. So he can observe the initial public key. Then he has the ability to participate in registration and recovery ceremonies. This corresponds to the case where a user registers with the service that is hosted by the adversary. So the adversary can observe the derivation of public keys and also signatures that are created during the recovery process. Additionally, the adversary has access to a leak oracle, which can leak the associated secrets with the derived public keys that you can observe during the registration phases. To win the game, the adversary has to perform a successful account recovery where he's not authorized to do so. After observing all the registration ceremonies, he can pick a session for which he wants to perform recovery. He will receive the recovery information and an associated challenge. And his job is to somehow forge a valid signature on the response. This is an update of the previous notion, which was brought forward by Freeman et al., which worked slightly different. They also had a similar functionality of observing and participating in the protocol. However, they had different levels of adversary strength. There was a strong and a weak adversary and an honest and a dishonest adversary. And the leak oracle was only available to the stronger version of the adversary. Furthermore, the winning condition was different. So it was also not called authentication security, but it was called key security and focused more on the security of the derived secret key. The adversary won if it outputs a valid derived public key with the corresponding derived secret key and recovery information. We argue that this is too strong, since for successful recovery, it is sufficient to generate a signature that validates under the derived public key, and it is not strictly necessary to also derive the secret key. The other important security notion is unlinkability. Unlinkability's job is to preserve the privacy of a user when he's registering with different services. So colluding different services should not be able to recognize that the user is using the same authenticator. This can be useful if one wants to stay anonymous by using different usernames or even have different accounts at the same service. So in the unlinkability security game, it's a left or right style game. The adversary first observes the initial pairing of two different primary authenticators with a backup authenticator. So he receives access to two different initial public keys. Using these initial public keys, he can then simulate as many registration processes as he wants. As we have seen, the derivation of public keys does not take any secret inputs. So he can simulate this for himself. And to aid him, there is also an oracle which leaks the corresponding secret keys that correspond to the public keys he can simulate himself. And finally, the adversary gets a single challenge query where he receives a derived public key with the corresponding derived secret key and recovery information, and has to decide if this was derived from the yellow or from the blue authenticator. The previous notion of unlinkability did not have the two oracles, and also the challenge query worked differently. He was allowed to have multiple challenge queries where he was talking to either an actual authenticator or was receiving public and secret keys that were sampled at random from the same distribution. Note that the adversary does not get access here to the recovery information, which unfortunately allows for a trivial attack because it is allowed to encode some information on the initial public key in the recovery material. This was independently observed by Stiebiler and Wilson at AJCCS this year. I will now introduce our construction, how we construct post-quantum asynchronous remote key generation for FIDO2. The pairing, for the initial pairing, which happens once, just requires the key generation of a CAM key pair. And the CAM public key is then sent from the backup authenticator to the primary authenticator, while the backup authenticator stores the corresponding secret key. During the registration phases, the primary authenticator has to execute the derived public key algorithm, where he uses the CAM public key, which he received from the backup authenticator, to first obtain some key. He then uses a key derivation function to smooth this key to obtain some randomness, which he can then use to deterministically execute some signature key generation giving him the derived public key and the derived secret key. The derived secret key is then discarded, and the recovery information is composed of the CAM ciphertext as well as some auxiliary information, which is not relevant to the security. And it then sends the derived public key as well as the recovery information to the relying party. During recovery, the backup authenticator, which has access to the corresponding CAM secret key, now has to execute the derived secret key algorithm, where he first performs the decapsulation on the CAM ciphertext to receive a key, then he uses the same key derivation function to obtain the same randomness, and then deterministically generate the exact same key pair as the primary authenticator has done before. So knowing this derived secret key, he can now successfully perform the recovery. I will now talk about the security and how to actually instantiate this in a post-quantum setting. For authentication security, we've been able to achieve this if we have a key encapsulation mechanism that is int CCA secure. We need a signature that is essentially unforgeable under chosen message attacks, and we need a key derivation function that behaves like a pseudo-random function. We lose an additional factor of Q that corresponds to the maximum number of calls to the derived public key oracle in the authentication security game. For unlinkability, we have been able to reduce this directly to the anonymity in the presence of a decapsulation oracle of a CAM scheme, which is a non-standard assumption that basically says that the ciphertext obtained during encapsulation does not leak any information on the public key used during the encapsulation oracle, even in the presence of a decapsulation oracle. Now, this anonymity under a decapsulation oracle is a non-standard assumption, but luckily Kyber or MLCAM does have this property along with the NCCA security that we require. Furthermore, all post-quantum signatures that are currently being standardized do provide the extension unforgeability. And for the key derivation function, it's a symmetric primitive, so you only have to be careful with the key length to achieve security in a post-quantum setting. So to conclude, we have tailored the security games more closely to the FIDO2 settings. We have shown a generic construction from standard primitives, how to instantiate this. And then we show that this is actually secure in a post-quantum setting. With this, I conclude my talk and would be happy to take some questions.
Thank you very much for the nice talk. Are there any questions? No? So I have a question. So how does your protocol compare to this work by Stabile and Wilson that you mentioned in terms of security and the efficiency of your protocol?
Regarding efficiency, we have not performed benchmarks yet. I have a student that's currently working on this. Stabile and Wilson have used a different approach and needed some new security assumptions, but I'm not too certain on the details. So I don't want to make any wrong claims here, but I'd be happy to discuss this offline.
Okay. Yeah. All right. Yeah. So also for your assumptions on your primitives, so for the signature scheme, do you only need standard unforgeability, or do you need strong unforgeability?
No, we just need the standard extension unforgeability.
Okay. Yep. All right. Thank you. Any other questions? No. Yeah. In that case, yeah. Let's thank Sebastian again. Thank you. Okay. So Do we have the next speaker, Adrian Winsott? Yep. So the next paper is titled Min-Rank Gabidulin Encryption Scheme on Matrix Codes. The authors are Nicolas Aragon, Elaine Couvrier, Victor Dicerin, Philippe Gabory, and Adrian Winsott. And Adrian will give the talk. Thank you, Adrian.
So, hello everyone. Thank you for the introduction. I will present to you a work I did in collaboration with Nicolas Aragon, Alain Couvreur, Victor Dizerin, and Philippe Gabory. I will talk about an encryption scheme which relies on the Michaelis frame. So, what is the Michaelis frame? The Michaelis frame is a generic framework which allows to design efficient encryption schemes. Where you take an error correcting code for which you know an efficient algorithm of decoding, and you both use this code to encrypt and decrypt the ciphertext. So it has a main advantage. It's because you have a very small ciphertext, since it's only a noisy vector, but you have two main drawbacks. The first is you have a very big public key, since it is often the generator matrix of the code. And the other drawback is you have a structured secret code. So there are many attacks which allow to retrieve the original secret code from the masked code you have in your public key. But it's still the Michaelis frame which allows the smaller ciphertext. So we will consider Gabidulin codes. So in the context of rank metric, the Gabidulin codes have a very great power of decoding. There are some crypto systems, for example, the GPT crypto system, which have been proposed with Gabidulin codes. The problem is it's a very structured code, so there are many efficient structural attacks. For example, the overbreak attacks break all the variants of the GPT crypto system. But the overbreak attacks use the FQM linearity of the code. So our idea is to take a vector code, a Gabidulin vector code, and to turn it into a matrix code, which is just FQ linear. So we break the FQM linearity, which makes the overbreak and all the efficient attacks completely inefficient. So it results very efficient scheme with a very small ciphertext, even smaller than the classic Michaelis, which has been proposed to the NIST, and also a smaller public key. And we have a smaller ciphertext to all the main proposition to the NIST. So firstly, I will begin with some mathematical preliminaries. So the rank metric makes sense in an extension field. So you consider Q a prime number of a power of a prime, and you consider the extension field FQM. So FQM is a FQ vectorial space. So there exists a FQ basis gamma, and we define the application psi gamma, which only consists on write the coordinates of x in this basis gamma. Then we can extend, of course, the definition of psi gamma to vectors. So if we have vectors of n elements in FQM, so we obtain a matrix with m rows and n columns. So it allows to define the rank metric. So we will call the support of a vector the FQ vectorial space, which is spanned by its coordinates, which lives in FQM. And the rank of x, so its weight, is equal to the dimension of the support. And the rank weight of a vector is also equal to the rank of the matrix psi gamma de x, psi gamma of x. And of course, the rank of a vector does not depend of the basis gamma, since if we take two bases beta and gamma, you have to multiply by left by an invertible matrix at coefficients in FQ, and invertible matrix at coefficients in FQ are the isometries for the rank matrix, so it does not change the rank of the matrix. So matrix codes is just a FQ vectorial subspace of matrices at coefficients in FQ that we endowed with rank metric. So the rank metric for a matrix is just his rank. And thanks to the application psi gamma, we can turn a vector code into a matrix code only by considering the image of a vector code by the application psi gamma. So if we have a code of dimension k and length n, we obtain a matrix code with the following parameters. So by definition of psi gamma, we obtain matrices of size m times n, and the dimension is not k, is mk, because of we lost the FQM linearity. So since we have to consider it as a FQ vectorial space, and it has dimension mk as FQ vectorial space, since it has a dimension k as FQM vectorial space. So now we have matrix codes. I will explain how to encrypt with the matrix code. So imagine we have a matrix code of dimension k. It's like a vector codes. So if you want to encode a vector x, you compute a linear combination whose coefficients are those of x, and you had a matrix E of small rank, where R is the decoding capacity of the code. And then to decrypt the word y, it is exactly the well-known min-rank problem, which has been very studied. So from y, the word y and the matrices mi, the objective is to retrieve x or the error, which is equivalent, and this problem is known to be NP-complete. So next, we will define the dual of a matrix code. So to do that, we need the application unfold. So the application unfold does not change the coefficients, it changes only the representation of the matrix. So you have a matrix and you write it as an only vector. So the first coefficients are the source of the first column, the next coefficients are source of the second column, etc. So it only changes the representation of the matrix. And we have fold, which is the invert of the unfold map. So thanks to the unfold map, we are able to define a matrix code thanks to an only generator matrix by unfolded on the line. And we obtain a number of rows which is equal to k, and a number of columns equals to mn. And it's allowed to define a parity check matrix, which is the matrix at coefficients in FQ, which is orthogonal to all the rows of J. And it allows to define a dual code. And the dual code, you can consider the basis of the dual code as the folded line of the parity check matrix. Then, to define the Gabby-Doolin codes, I will explain what are Q polynomials. So the Q polynomials are special polynomials since only the coefficients which are a power of Q are non-zero. So it does mean it's linear combinations of compositions of the Frobenius. So a Q polynomial is a linear application. And then we can use it to define the Gabby-Doolin codes, which are the adaptations of Reed-Solomon codes in the context of rank metric. So like in Reed-Solomon, you take a vector of evaluation points, and rather than consider the evaluation of standard polynomials, you consider the evaluations of Q polynomials. And like for the Reed-Solomon codes, it has a decoding capacity of n minus k divided by 2. So now we have these preliminaries. I will explain what is our new scheme. So I will begin to present our new masking on a matrix code. So if we have a basis of a matrix code, we will add some rows and columns of random coefficients to all elements of the basis. So different, of course, different coefficients to each element of the basis. And then, so that we represent by matrices R, R prime, and R second. And we multiply by invertible matrices P and Q to propagate all the coefficients in the matrices. And the trapdoor so relies on the min-rank and the code equivalence problems. So we will now, thanks to this masking, we will now define what we call an enhanced Gabby-Doolin matrix code. So if we consider a Gabby-Doolin codes of length R dimension K, And we just sample a basis, an FQ basis of FQM. So we compute the image of J by psi gamma. So we obtain a matrix Gaby-Dulin code, and then we apply the masking that I just defined. So it follows a matrix code whose matrix have n plus L1 lines and n plus rows, and n plus L2 columns, and dimension km, since our Gaby-Dulin codes had dimension k. So now we will apply the Michaelis frame to matrix code to our Gaby-Dulin matrix code. So what we do, we begin to sample a Gaby-Dulin code with decoding capacity equal to R. Then we sample a random basis of FQM, and we compute the matrix code psi gamma J. And then we apply the transformation. So we add random coefficients and multiply by random matrices P and Q. And as public K, we have the masked code, so the code we have construct, and you keep secret the original Gaby-Dulin code, the basis gamma on which we will write the matrix code, and the invertible matrices P and Q. So how we encrypt? So it's exactly I just defined previously. So you have a basis of your code, and if your message is new, you just compute a linear combinations of a basis, and you add a random error of rank inferior or equal to R. And you add to the linear combination, and it's your ciphertext. So how we decrypt? Firstly, we begin to multiply at right and left by the inverse of P and Q. So we retrieve a linear combination of non-scrambled matrices plus an error to which we multiply by P as the inverse of P and Q. But as I previously said, P and Q are invertible matrices, so the multiplication by right and left does not change the rank of the error E, because invertible matrices, the multiplication by invertible matrices are isometries in rank metric. So what we do, we just have to truncate the L1 and L2 last columns, L1 first rows, last rows, and L2 last columns, and we obtain a resulting matrix. And by computing the inverse of the application psi gamma on this matrix M, we retrieve a noisy code word of J. So we can apply the decoding algorithm of Gaby-Dulin codes to retrieve the error E, and then by solving a linear system, we are able to retrieve all the coefficients of mu. So that was for the Michaelis frame. So there was also a variant, the Niederreiter frame, sorry. So the Niederreiter frame consists on, rather than put in the public K the generator matrix J, put parity check matrix H, so a basis of the dual code. So it's exactly the same like in matrix codes than in vector codes. The message to encrypt is a matrix of small rank, and the ciphertext is the associated syndrome. So we have, for an equivalent security, a ciphertext of smaller size, sorry, because syndromes are always smaller than code words. So now I presented you the scheme. I represented you the security of this. So we claim our scheme is 1 minus CPA under the assumption that there exists no efficient algorithm to solve the min rank problem, and there is no efficient algorithm to solve to distinguish a random code to a valid public key. So I will just recall the main attacks against min rank. It's a problem which has been often studied, but I will just recall the main attacks. The first is a combinatorial attack, the kernel attack. So you sample random vectors, and you hope that all your vectors belong to the kernel of the error. And if it's the case, you can deduce E by solving a linear system of equations. And the second is an algebraical attack, the support minors attack. So you know you have a matrix which has rank less than R. So if you have a matrix of rank less than R, so all the minors of size more than R are equal to 0. So you can deduce a multivariate system of equations whose unknowns are the mu e, and you can solve it to retrieve it. So now I will more carefully speak about the attacks on the K, which allow to distinguish a random code from a valid K. So matrix Gabby code which has been masked with the masking we propose. So firstly, I will define the left stabilizer algebra. So the left stabilizer algebra is a set of matrices such that when we multiply at left the code, you obtain a new code which is included in the first. And we can see in the case of vector code which has been turned into matrix codes, the left stabilizer algebra at dimension at less equal to m or more, because of you have at least all the matrices which represents the multiplication by alpha, alpha being all the elements of FQM, which have been written in basis gamma. If CMAT would be a random code, so with very high probability, the stabilizer would have dimension 1 because you should have only the identity matrix and the vector span and the vector space it spans. And since the left stabilizer algebra is very easy to compute, you have a very efficient distinguisher. It allows to construct an efficient distinguisher between these random codes and the masked Gabby-Dulin codes. So firstly, I will speak about the non-scrubble basis. So our idea is to apply a projection map on both rows and color space of the public K of the public matrix code. Sorry. The goal is to get rid of the contributions of all the random coefficients. So we can see if you multiply by matrices which have this form, where U0 U is composed of invertible matrices on which you concatenate several L1 columns of zeros, and V is a random matrix to which you had some rows of zeros too. Then the code U times C0 times V is spanned by the matrices U0 times AI to V0, and by the properties of matrix Gabby-Dulin codes, you obtain UC0V is also a matrix Gabby-Dulin code, but with a different evaluation vector and a different basis. So we have to compute the number of arches of UV is approximately to this number. So when we think about the scramble basis, so when we multiply by P and Q at right and left, so the same reasoning can be made. So the only difference is that you have to guess a matrix which has the form U times the inverse of P, U times the inverse of P, and V which equal to V which has the form of the inverse of Q times V. And the matrix and the number of choices is still the same because you only multiply at right or left by an invertible matrix. So it allows to construct an efficient distinguisher. Since you have just to guess this matrix, we have this form, and then you just have to compute the left stabilizer of your new code, and you do that until you get a left stabilizer of dimension m or more. And the probability to finding a valid pair is this number, and we can deduce this as this complexity since the cost to compute the left stabilizer is negligible. So it results these parameters. So we can see our best propositions are for 128 bits of security are for small value of R. So with Gabby-Dulin codes which have an high dimension and some precision, our parameters are NIST compliant. So we consider also the 15 margin bits of security, I guess. So it's why we could compare as I saw in the beginning in my introduction, we could compare with the other scheme proposed to the NIST. Thank you for your attention.
Thank you very much, Adrian. Any questions? Yes, at the back. Do we have the microphone there?
Hello, thank you for the talk. So you said that the overbite-like attack didn't apply because you killed the FQTM linear structure, right?
Yeah.
But couldn't you have like a matrix version of that? Like, because I believe that if you consider the overbite to be the application of some Q polynomial on your Gabby-Doolin code, you could consider multiplying your the matrix of your matrix code by some matrix over FQ, which represents this FQ to the this Q polynomial. And you should have similar behaviors, right? The dimension of this code should be should grow linearly in the dimension instead of quadratically. So isn't it a distinguisher?
Do you mean when you, as a distinguisher, we choose the Gabellian structure of the matrix code? Of course, yes, there is a distinguisher which choose the right, the right stabilizer. Maybe is what you mean.
Yeah, maybe I.
Yeah. Yes, but it took no advantage when you compare with the distinguisher we have.
Okay.
Yes, the distinguisher which does not really exploit the Gabellian structure of the code is the better we have.
Okay, thank you.
Any other questions? Yep. At the back on the left.
Okay, I have two questions. And first, this scheme is OW CPA secure. CPA secure. So if you want to convert it into CCA, what is the difficulty level to convert it into CCA security? Ciphertext security.
I'm sorry, do you mean would have a better level of security?
Yeah, this is CPA secure scheme.
Yes, yes.
So I'm just asking whether it is achievable. CCA security, is it achievable or not?
We have exactly the same security than the classical Michaelis. So for example, in the Michaelis scheme, the hypotheses of security are very similar because you have the decoding problem. In our case, it's the minimum problem, and the case of existence of no distinguisher. So the hypotheses of security are the same as Michaelis.
Another thing is, if you use cycling code or dyadic code, we can reduce the public key size. Means your public key size means what is the comparison among those two?
It seems difficult because in the public key size, you will propagate all the random coefficients when you multiply by right and left by the invertible matrices. So it seems very difficult.
Oh, thank you.
Any other questions? So I have another question. So I think in the past there were some proposals for variants of Michaelis using Ritz-Solomon codes with over the Hamming metric. So I think there were some attacks on those. So did you look at to see if those can be extended to your min rank based scheme or?
Not really.
So yeah.
No, no, sorry.
Yeah. Okay. Yeah, that's all right. Okay. If there's no other questions, then yeah, let's thank the speaker again and Okay, we can move on to our next talk. Okay, so the next talk is titled A Tight Security Proof for Sphinx Plus, formally verified. The authors are Jess Meyers, Manuel Barbosa, Francois Dupressoir, Andreas Halsing,
Hello.
and Pierre-Yves Stroop. And the speaker will be Matthias. Thank you, Matthias.
Okay, let's see. Perfect. Okay. Okay, so hi everyone. My name is Matthias Meyers, and together with the author shown here on the slide, I've been working on the formal verification of a tight security proof for Sphinx Plus, which will be the topic of this talk. And so I will start with some context, beginning with the scheme of interest being Sphinx Plus. So Sphinx Plus, as you might know, is a stateless hash-based digital signature scheme that is post-quantum, so it's supposed to be secure against both quantum adversaries as well as classical adversaries, and has recently been standardized as SLH DSA by NIST as a result of the NIST post-quantum standardization process. However, despite being under heavy scrutiny due to this standardization process for several years, a mistake in its tight security proof was only discovered after 3 years and took 2 more years to for a fix to be published on paper, which might, of course, raise the question whether the new updated proof is actually secure or whether there are more undiscovered errors. Okay, so then the other part of the context here concerns formal verification, which is part of the field of computer-aided cryptography. And this field at least got partly established due to cryptography becoming increasingly more complex and leading to a higher likelihood of broken designs, proofs, and implementations of cryptography. And so computer-aided cryptography attempts to alleviate these issues through computers, essentially reducing the complexity of the manual verification effort and while consistently enforcing a high level of rigor. And in essence, this shifts the trust we have or gain in proofs to the trust we have or gain in the trusted computing base of the tools and frameworks that we use. And so for this form of verification effort, we opted to go for the Asiacrypt proof assistant, which is a tool aimed at formally verifying code-based game-playing security proofs in a computational model, while also having features that allow for extensive mathematical reasoning, as well as introducing modularity in your proofs, which can be quite convenient in reducing the complexity. Okay, and then for the purpose and contribution of this work, first and foremost, we attempt to increase the confidence we can have in the security of Sphinx Plus. And in particular, we do so by first essentially reconstructing the current tight security proof of Sphinx Plus in a very modular and granular way, which helps us to manage the complexity in a formal verification, as well as reuse some existing formal verification artifacts that have already formally verified a modular part of this proof. And then secondly, we actually formally verify this reconstructed proof, of course. And due to the modular approach that we take, we actually isolate a generic relation between hash function properties that we formally verify, which was published by Bernstein and Hulsing back in 2019. Okay, and then secondly, we aim to facilitate future formal verification endeavors by creating reusable libraries for concepts that were useful in this form of verification, specifically being binary or Merkle trees, as well as hash functions. And we also create a new sort of proof technique that can be used in sort of non-standard proofs of security in Asiacrypt. Okay, so that's it for the context for this work. So I will now go over a bit of the process for this formal verification. So the objective, as I said, is the formal verification of a tight security proof for Sphinx Plus, but in particular, we aim to prove the standard EU/CMA property for Sphinx Plus, and we base it on the hash function properties, viewing the hash functions as a black box. Okay, so the high-level approach we usually take in these kinds of formal verification endeavors is the following. So first, we construct a proof that is usually very detailed. So we do this without the tool, and we make it so detailed as to be able to use it as a proper guideline in the following steps in the form of verification, because the tool will eventually force you to be really detailed anyways. Then the second step is to formalize the context and the proof steps in the tool. And here you can think of things like parameters of the scheme itself, adversary classes, reduction adversaries. And this is also the main thing that in the end needs to be manually verified as well. Yeah, and then the final step is to actually formally verify the proof. So this is actually essentially using the tool to verify and validate that your proof steps that you formalized in the second step are actually correct and valid. Okay, so I will walk through these 3 high-level steps for this specific form verification effort, starting with the construction of the proof. But before showing the proof overview, I will give an overview of Sphinx Plus, so we actually know what the proof overview is talking about. So Sphinx Plus essentially combines 2 different schemes and a message compression step, and these 2 schemes being XMSS multi-tree or XMSS MT, of which Sphinx Plus uses 1 instance essentially, and Force, of which Sphinx Plus essentially uses multiple or many instances. And actually it's a fixed length variant of XMSS multi-tree that Sphinx Plus uses. Okay, so what are these 2 schemes then exactly? So XMSS multi-tree is in itself a tree of XMSS instances, where XMSS is a Merkle tree signature scheme, so it is a 1 tree in itself, making XMSS a tree of trees, XMSS multi-tree, sorry, a tree of trees, which is often referred to as a hypertree structure. And in Sphinx Plus, this is used to sign the public keys of the Force instances that Sphinx Plus uses. And then Force is essentially, instead of like a tree of trees, it's a sequence of Merkle trees. And in Sphinx Plus, there's 1 instance of Force per leaf of the XMSS multi-tree, hypertree. And in Sphinx Plus, this is used to actually sign the messages. Okay, so zooming in a bit on the actual workings of the scheme, the inner workings. So we start with XMSS, this part of XMSS multi-tree. And so XMSS, as I said, is a Merkle signature scheme, which means it combines a Merkle tree with a one-time signature scheme, and in XMSS's case, it's the Winternitz one-time signature scheme. And so there's an example instance here on the slide. So to generate such an instance, what you do is you generate the one-time signature key pairs, as many as there are leaves of a binary tree, I guess. So in this diagram or figure, there's the red keys are the secret keys of the one-time signature scheme, the green keys are the public keys. And then to create the leaves, we hash the public keys into the leaves, and then the rest of the layers of the Merkle tree is sort of iteratively constructed by taking 2 neighboring nodes and combining them and hashing them into their parent node, right? And then we do this layer by layer until we reach the root. Okay, and then a signature in XMSS consists of a signature on the message of the one-time signature scheme, of one of the one-time signature scheme instances, and then the authentication path of the leaf corresponding to the signing one-time signature instance. And an authentication path here consists of the sibling nodes of the path from the leaf, considered leaf, to the root, right? And intuitively in verification of a signature, this is used to sort of authenticate or verify that the one-time signature instance that was used to sign a message actually is part of this XMSS instance. Okay, so then combine XMSS MT, as I said, is a tree of XMSS instances. So it takes these XMSS instances that we saw and puts them in a tree structure. And so here, the bottom instances sign the messages, and in Sphinx Plus being Force public keys and not actual messages. And the intermediate instances sign the roots of the instances below. Right? And so here in the diagram, an example again, so all these triangles are XMSS instances, which are the thing that we saw in the previous slide. Okay, and then the signature for XMSS MT is essentially just the XMSS signatures from the signing instance in the bottom layer to the root instance. All right, and then Sphinx Plus combines, takes this XMSS MT structure and just adds a Force instance for each leaf of the hypertree, and as well as a message compression step, of course. Okay, and then the signing procedure essentially proceeds as follows. It takes an arbitrary like message, it compresses this, which gives a compressed message as well as an index. This index points to one of the Force instances on the bottom layer of the hypertree. This instance is then used to sign the compressed message, and then finally the XMSS MT is used to sign the public key of the force instance that we use to sign the message. And so here in the diagram, an example again. So here in this case, the red keys are the force secret keys, force public keys are the green keys. Then these lines represent signing of the public key by the bottom layer instances of XMSS. And these intermediate lines represent signing the roots of the intermediate layer XMSS instances to the bottom layers. Again, then the signature is just the force signature on the message as well as the XMSS signature on the force public key. These both together are a Sphinx plus signature. Okay, and then before actually going to the proof, there's one more additional modularization step that we did to accommodate like the modularization of our proof, which is we introduced an auxiliary multi-instance force scheme, which combines all the force instances essentially in a Sphinx Plus instance, as well as the message compression step. And then Sphinx Plus essentially becomes XMSS MT plus this multi-instance force scheme. And so in the diagram, this then looks like this. So M-force encapsulates sort of or encompasses all these force instances on the bottom layer as well as the message compression. And XMSS MT is just XMSS MT as it was. Okay, so then knowing this, the proof structure is as follows. So on the top here of this diagram, we see the final goal, sort of, which is the EUF-CMA property of Sphinx Plus. And then if we go one layer down, we see that we sort of show that this is implied by 4 different properties, which are two of which are PRF properties for a nonce generation function, as well as a secret key generation function. And then on the left-hand side, we have the an EUF-CMA variant for the fixed length XMSS multitree that Sphinx Plus uses. And on the right-hand side, we have the EUF-CMA property of the M-force multi-instance force scheme that Sphinx Plus uses. Okay, and then looking at the fixed length XMSS MT here on the left-hand side, we then in turn show that this is implied by 2 target collision resistance properties for the function that constructs the leaves from the one-time signature public key. And the function that constructs the actual inner nodes of the Merkle trees, as well as a multi-instance EUF-CMA variant for the one-time signature scheme that XMSS uses, which we then in turn show to be implied by 3 properties of the hash function that it uses in its operations, which are an undetectability property, a pre-image property, and a target collision resistance property. And so actually this part here, the multi-instance EUF-CMA variant for the WOTS, that this is implied by these 3 properties of its hash function that it uses is an artifact that we reuse from previous work that formally verified single instance XMSS. And okay, then going to the right-hand side, we have the M-force EUF-CMA, and we show that this is implied by 4 hash function properties, one being the ITSR property, it's called for the message compression function, a variant of pre-image resistance for the hash function that's used to construct the leaves of the Merkle trees, and as well as 2 target collision resistance properties for the function to construct the inner nodes of the Merkle trees, as well as the hash function that is used to compress the Merkle tree roots into the public keys of a force instance. And then finally, we show that this variant of pre-image resistance for this hash function that constructs the leaves is implied by the a decisional version of the second pre-image resistance and target collision resistance property. And so this is the generic relation that I mentioned in the introduction that we also formally verify. Yeah. Okay, so that's sort of the first step of constructing the proof. And then the second step is the formalization of the context and the proof steps. And here, I won't really go into many details, but here what you can think of is for the context, you can, there's like the parameters, the types, function, and distributions, which is where our binary and Merkle tree library comes in, as well as the specification of the schemes. And for the proof steps, you can think of things like specifying security notion hardness assumptions, which is where our generic hash function library comes in. the adversary classes and reduction adversaries, the games in your game hopping proof, and as well as the probability statements that relates these games. Yes. Okay, and then the last step of this overall process is the actual formal verification of the proof. And so here I will highlight a few points of difficulty. And for more details, I would refer you to the paper or the code. Okay, so a first point of difficulty was actually this, or occurred in this generic relation of this, between these hash function properties of the leaf hash in the mForce proof. And the reason why this was a point of difficulty was that this isn't actually a typical standard security proof that goes by like direct reduction or a sequence of game hops, but rather like does a detailed multi-dimensional analysis of like the probability space. And then some of these probabilities that you have to analyze are sort of conditional probabilities that depend on the behavior of the adversary in the game, which is something that is not inherently easy or supported in Asiacrypt. So we had to, this is where we devised sort of a new sort of proof technique where we combine different logics of Asiacrypt to actually still achieve this. Right, and then the other point of difficulty actually occurred both in a proof for XMSS multi-tree as well as the mForce. And this is actually that in the reductions to target collision resistance for the hash function property, or for the hash function that construct the inner nodes of the Merkle tree, we actually have to do a node-by-node construction of the whole structure of the schemes through oracle calls, which you then also have to sort of like maintain invariance over and reason about over this whole structure, to eventually then extract one collision, one node for the collision of in the authentication path, which is quite cumbersome to do and difficult to do as well. Yeah, so then I will conclude with some future work and summary. So for future work, so what we did now is to prove the EUFUMA property of strings plus based on the assumed properties of the hash functions, where the hash functions are left as like a black box. So a natural sort of next step would be to actually look at the standard sort of like the default or often used instantiations of these hash functions, and then analyze these, whether these actually satisfy these properties or whether it's reasonable to assume so. And then a second thing one can always do as an extension of projects like this is to actually create like an implementation that is like actually a cryptographic implementation, so an efficient one, that you then actually prove or formally verify to be functionally correct to the specification that we prove secure in this work, which then sort of indirectly proves your implementation to also satisfy the desired security. And then lastly, something that is always useful to do as future work is to still improve the tools that we use. So create libraries and add additional features. And actually the Formosa Crypto project that I listed here is one such project that attempts to achieve this by bringing together like developers and users to improve our tools, among which Asiacrypt. Oh, wait. And so for more information, you can go to this link if you're interested. Okay, and then so finally some summary and some basic statistics for people that are interested in this. So what do we do? Again, we formally verify the tight security proof of strings plus by first reconstructing the original tight security proof and then actually formally verifying it. And we've attempted to facilitate future formal verification by creating new or improving existing Asiacrypt libraries that can be reused in similar situations or where similar concepts are used, as well as a new proof technique that can be used in cases where there's a similarly non-standard proof. And then the total, so for some basic statistics, for people who are curious, so the effort that this took, we have one main sort of developer working on the code and 4 people supporting / guiding in the process, where we worked on this for 7 months, where the main developer was also part-time working on this. And then the eventual output was approximately 70,000 lines of Asiacrypt code, but of which, most of which is, of course, all verified by the tool. And the only thing that is still left to sort of manually be verified are the things like the specification, essentially. So the specification of the scheme, the types, the distributions, the adversaries, as well as the actual probability statements, the security statements. And so that concludes my talk. I'm a bit quick, I think, but if there are any questions, I will be happy to take them now.
Thank you very much, Matthias. Any questions? No? Yes. Yeah, we have the microphone coming. Yeah.
So to prove like similar, I mean the proof correctness for similar other hash-based crypto systems, for example, like how much of this effort is reusable?
Yeah, good question. So, yeah, so there's at least like a couple libraries that we had, right? So we had the hash function libraries that is quite comprehensive, I would say, in terms of like the definitions of both like the hash function itself as well as the security properties. And we also then have several proofs between relations, I suppose. So this is definitely reusable. Then you also have, so what you typically see in hash function based schemes, of course, you have the Merkle trees and the binary trees, which we also have libraries for that are also quite comprehensive, I would say. So yeah, these are the parts that you can reuse, and yeah, I think there's a decent amount that can be reused here. I mean, it has to of course be adapted to like the specific context, but yeah.
Thank you very much.
Any other questions? No other questions? I have also a question. So, yeah, I mean, in terms of the tightness of the reduction, so, so first of all, is the tightness the same as the earlier manual proof in your formally verified? And
Give or take 1 bit of security.
okay.
So there's one. Okay, wait. So the modularity of the proof actually. So I talked to okay, well, I have a lot of animations. We can almost, yes, good. Yeah, so in terms of additional terms, the only additional term there is from the, it is the TCR term here. Okay, yes, we have 3 hash there, TCR on the left, and also 3 hash TCR on the right. And in the manual proof that already existed, there was not like this modularity. So this 3 hash is actually the same function, right? So we have 2 terms now instead of like 1. And even though like the number of queries are split between these, the eventual bound that is proven in the original, the eventual thing that you bound this term with doesn't actually depend on these queries. So we just get an additional bound. But this is, again, give or take 1 bit of security, if I'm not mistaken. So, so technically slightly worse, but yeah.
Yeah,
1 bit.
But it's more modular.
Yeah.
And I mean, the actual tightness, I mean, how tight is it? Like, do you have any kind of, I mean, do you have attacks that actually get very close to the bound, or?
Sorry, again?
So, I mean, how tight do you think the proof is? I mean, compared to attacks that you know about, or is there no gap at all? Or I mean,
that's a good question. That's a good question. Against attack, I wouldn't. I don't know. I would have
Okay.
to think.
All
There's
right.
no, we didn't look into any attacks or anything. No.
Okay.
And I'm also not aware, maybe they did this for the original proof. And then it should be, I mean, it should be close to whatever the original analysis also had, because our proof is almost the same, except for
Yeah,
this
yeah,
one basic term. So, but I'm not, yeah, I haven't looked into this. No,
Okay. Yeah. All right. Thank you.
thank you.
All right. Any other questions? Oh, no, if not, then yeah, let's thank Matthias again. So yeah, I think this is the end of the session. We have we're a few minutes early, but yeah,